with exponential growth, exponential decay, compounding interest problems that are compounded continuously, as opposed to compounded monthly or daily or yearly and something like that. It is a very simple thing to use. We treat it a lot of times like it's a variable. It has properties to it that works the same way as growth or decay when we graph them. Since it is an approximation, a lot of it comes with using the calculator, and it literally is pressing a button. Okay? The E button is at, you gotta press the right button. You
didn't add that at first.
I know, I'm sorry. And you press second divide, and that gives you the value of E. Okay? That's good.
What if it's going towards negative? Is it like negative 20, or is it like
We
2 or something?
think about what this end value meant. It's the number of times things were compounding.
Oh,
You want,
okay.
you see what I'm saying?
What if you're going back in time?
We're not doing 88 in a DeLorean. Yes, ma'am.
So like the top thing, you have like 1 plus 1 over n. Is this where does the 1 over n come in? Like why isn't it r over n?
They're looking at it, it comes from the rate being 1.
So if this is only if the
Yeah.
rate is 1.
Yeah, it's not that it's going to tell you the rate is 1, you have to use this value. All I'm showing you here is where does this come from? It comes from a stem of this. Okay, it comes from working with this value as n gets infinitely larger. That's what it just wound up being. Hey, look, it's approaching this value. Just like the relationship of the diameter to the circumference is pi. It's the same idea.
So can r be any number or no?
Excuse me. In this case, when we're looking at straight value of E, r is going to be 1. Okay. But don't worry, you don't need to know that. Okay. You don't need to know that. It really becomes way more complex than what you guys need to worry about whatsoever. It's a great question, but you don't need to worry about it. Right? What I'm saying here is the stuff that we're going to work with is, let me get to it, using exponent rules with e's. I mean, E, and it is e's, yes. So if I'm looking at using this value of E to the 3rd power times the value of E to the 4th power, what does it get? All those exponent rules apply. So it's nothing more than, you can treat it almost as a variable for the way the properties work because it's the same base. It's got the base of E raised to an exponent times something else with the base of E raised to another exponent. You add those exponents, just like we've done before. What?
What's that help with? Just like when you do it out, you get 1,096 for infinity.
Remember,
What
this
is
value of E is 2.7198628. I don't know. 867-534. 903-782. 8675 309. Thank you. See, maybe caught up on that one. Oh, remind me to show you something cool one of these days. Not today.
Show us some date on
this one.
Show us some Thursday.
It is. It's really cool. And I'll show you.
What is it?
How will we remind you if we don't know what it is?
Put a calendar reminder in your phone.
How are we going to just tell you to show us something cool and you're going to know exactly what we need?
You're gonna do something.
Because I know what it is.
Do you even know what you're talking? Like, do you have something in mind, or are you
Yes!
saying
I'm fine. For the love of God, I'll show you right now.
Oh man, let's write it out. Dang it.
You guys are all like, oh my God, what's it going to do?
It's not cool. It's probably not even cool.
It's probably not really cool and you're right, so you'll get over it.
It's going to do something. It's going to be like, that was Jenny's constant or something like that.
I think that's the first time I've ever been right.
Like yeah.
Put that in your calculator.
Guys, don't spoil it. I will.
Yeah, do not say anything.
No.
Just laugh.
Wait, as you did. Second. Wait, guys.
Where's pie?
It's
I
above
see it.
the carrot.
I'm good.
Second carrot.
You didn't even do it, so how can you even stand off me? You are barred from saying bad things about me for the next 7 days.
It's 8, 6, 7, 5. Okay, what does it do?
Not to say anything. 8, 6, 7, 5. Oh my god.
Oh, I get it. Thanks, Brad, for making completely. But then there's like, oh, how important.
Alright, what is... The fact she just says,
That's a good
oh,
reminder. I'm gonna keep that.
5, or 10 e to the third over 5e squared, what do you get?
2e. 2e and not to e.
Oh, there it is. 2e or not 2e.
This man would make that 2B joke.
Oh man, this is really unenjoyable. The quantity 3e to the negative 4x all squared, what do you do?
Multiply out the 2.
You distribute out your squares. It's not square root.
Oh yeah.
Yeah, that's fine.
So you'd have 9e to the negative 8x.
9 squared? 9 squared?
So it's 9 over e to the 8x. Because that variable, that exponent was not happy, okay? Now there's a, there's a time to have a negative exponent, and a time not to have a negative exponent when you're dealing with the values of e. No.
We got to rationalize.
Anyway,
Why'd you throw a
That was
marker at me?
dangerous.
no it wasn't.
Right on the window.
What happens here,
Yeah.
if you have a problem where it says simplify, you try to make sure you wind up with non-negative exponents. The reason that you will see a negative exponent is when you graph, okay? And that's where the next step of these things come into play. The negative exponents in graph, yes, I know. We get to it. You can press buttons in your calculator, right?
No.
No, I'm sure. Well, I know you have problems, but that's besides me.
I'll come into flex.
Don't write this down. Don't write this down.
Don't write this down. What happens here is that you get this generic form of an equation when you're dealing with E. And it mirrors out. It mirrors out the exact same idea of what we did last week of the parent function of exponential growth or exponential decay. Remember, the value of E is nothing more than some crummy decimal. So this is the same basic idea of y equals a times b to the x. Okay? Where your b value is e to the r. All right? Now, what happens here is that these graphs mirror the exact same thing as exponential growth or exponential decay, but it's in relation to the value of r. If the value of r is positive, it mirrors a growth function. If it's negative, it mirrors decay. So you plot it out the same way. Remember, growth functions can either go up and to the right or down and to the right, depending upon what?
B.
A. Depends on A. A is positive, it's going up and right. If A is negative, it's going down and right. Okay? It mirrors the same idea. If it's a decay problem, that means your R value was negative, and then you would either be going up and left or down and left, depending upon A again. But what happens now is when you have to graph these, it's very difficult to graph an E function because of the fact that it's a decimal approximation of 2 and change. So it's not like when we did growth and decay where we were able to substitute in -2, -1, 0, 1, and 2, work with the fractions and do all that work. It was work, but it wasn't awful. Here, you kind of are reliant upon having to use a calculator. Let me show you what happens. If we take a function like this, y equals 2 times e to the 0.75x, we know that the value of a is what? 2. I know that the value of a is going to be 2. And my r value is 0.75. So is it positive or negative?
Positive.
So is this going to mirror a growth graph or a decay graph? So is this going to go up and right or is it going to go down and right? It's got to go up and to the right. So I know it's got to look like this somehow, some way. Okay? So what do? Well, think about what exponents were. What is anything to the 0 power? 1. So if I use x is equal to 0, don't I get my y-intercept? Isn't my y-intercept still at A?
Yeah.
Still at A. So I know my y-intercept is still at A, which is 2. Okay? Since this is still mirroring the idea of a growth or a decay, where is, since there's no h or k here, where's my horizontal asymptote? Is it y equals 0 or x equals 0?
Why?
It's at y equals 0. So I still have an asymptote at y equals 0.
It's a horizontal, right?
Yes, sir. And now it's just a matter of getting another point. And this is where you have to use your calculator. Okay? You got to use your calculator. So you put this function in. Y equals
2e.
2
e to the
0.75. And just go to your table. And notice how you're just getting all crummy decimals except for
2.
at the y-intercept. All right? It's okay. It does make you uncomfortable, and that's all right, because you know that you have ordered pairs. And all you have to do is just, well, you write down a pair of ordered pairs. 0 and 2, and the other one is at 1 and 4 and change. You want to get rambunctious? The next one's at 2 and almost 9. And there's your graph.
That's it?
That's it. You have to be able to use a calculator to graph graphs. Yes, sir?
So why can't we just put it into the graph and then draw it?
Because I want ordered pairs.
So
What's
when
up?
you like do some homework,
Yeah. Give me.
you say like 4 and G. No, like this
No, I don't
would be
need-
so much easier for us.
No, what I want, and that's what's nice about these things here. What I want you to be able to give me is you're always going to have one clean ordered pair. This one's clean because there's no h and k. And I'll do another example here with an h and a k, and you'll still see you're going to have one clean set of ordered pairs. I want the clean ordered pair. This one is 0 and 2, and the other one, well, 1 and 4.2. That's fine. That's it. And I've got my my horizontal asymptote at y equals 0, and I've got my curve showing the direction. Yeah.
Where's the domain range?
Good question. What's your domain?
All the numbers.
What's your range?
Numbers greater than 1.
Because that's exactly what we did with growth and decay problems. Because it's still a growth or a decay problem. All right. This is actually just easier because values calculator. All right. Let me show you one with an h and a k. What's that?
Oh, no.
What happens when you have h and k then? So I have e to the negative 0.5 times the quantity x minus 2, all plus 1. So I'm going to label out what my a and the h and the k's are, just like I have before. I'm going to start with my a value, in this case, is 1. What do you think the parent function of this is going to be? Yep. My parent function is y equals 1 times e to the negative 0.5 x. That's the parent function. So I'm going to graph my parent function and then shift it to get my other set of ordered pairs. So my parent function has a y-intercept where? At 1. The a value. All right. So y-intercept an a value of 1. I know that this is decay. My a value is positive, so which direction is this going to be moving? Yeah,
Up and to the left.
it's going to be moving up to the left, okay? I know it's got to be going up and to the left. So go to your calculator, get your secondary point.
Are we supposed to write down our H and K?
I'll show you how it comes into play. It's really quite simple. What was it? 1 times e to the negative 0.5x, I believe? Yeah. So now I know I'm moving to the left. So I have my y-intercept at 1. My next value is at -1 and 1.6? Parent function has a horizontal asymptote at y equals 0. And it's doing that. And now you have an h and a k. Your h and k in this case is what? Good. So it's got to move what direction? Perfect. See how it's x minus 2 and then it's plus 1? So your h is 2 and your k is 1. So to these values, all you have to do is move them over 2 and up 1. Over 2, up 1. Over 2, up 1. There's your solid. Where's your new asymptote? Thanks for saying that. It's y equals 1 is your new asymptote. And your ordered pairs, see how you still went with the clean ordered pair after the shift?
Yeah.
You're just moving your y-intercept up and over. The ordered pairs are at 2 and 1. And this is at 1 and, what would that be? It was 1.6 and change, so it's 2.6 and change. And that's all it is. Okay? It is. And when you're working with these E-graphs, they usually are, because all you have to be able to do is find the parent function's y-intercept and shift it. Okay? That's really all it is.
The range is y is greater than 1.
Your range is y is greater than 1, and what's your domain? Good. Yep, see how it mirrors the exact same thing as growth and decay? It does the same thing. That k value still bounds your range, and your x value is not bounded for your domain. Really, it's really all there is. Okay. The last bit. Oh, I thought you meant for graphing. Yeah, that's really all there is for graphing. The last little bit is when this comes into play with interest problems. The difference between what you guys did yesterday with your interest problems is that you were working with, they were compounding monthly, daily, semi-annually, quarterly. They were telling you a specific amount of time that the interest would compound. Well, as your interest compounds more and more and more, it's approaching that infinite, it's compounding continuously. That's where this E value comes into play. So if it says it's compounding continuously, you use PERT. Or if you have dandruff, you use PERT. I know, and that's okay.
I'm gonna make my firstborn child. I like how we stop.
Plausible deniability. So again,
Mr. Murphy said, damn it.
so really, in all honesty, guys, the only difference that you're going to see when when these problems are worded out, it'll say compounding continuously, or it's going to say compounded monthly or something like that. If it says compounding continuously, you have to use PERT. I got a story for all occasions, you know? I'm like that crazy uncle that nobody wants to talk to. I mean, it's pretty cool. No, it's not.
Everyone was like, I need you to shut up right
No, everybody's awesome.
I don't get
Now we're going to use
Now, take a look at, see how it's worded differently here. You deposit $1,000 in an account that pays 8% and interest is compounding continuously. That just throws the red flag up that you use PERT. You're not going to get over this, are you?
Very
so
funny.
funny. Wait, why is it?
Ah, boo.
Do it again.
Why is it here again? What is
He said it was a very PERT-y problem.
Ah.
Ah. Since times 1 is too easy, let's say it's after 25
I
years.
still don't get why we use PERT in this situation compared to the regular.
PERT says no.
The reason we're using PERT in this problem is because it's compounding continuously. If it wasn't compounding continuously, we'd say it's compounding quarterly, or it's a
Oh.
monthly.
What does that mean, like every day or every
Yeah, it's just,
second?
it's always building upon itself.
Okay.
All right, it's always building, because remember, as the end value gets to be larger, the number of times it's compounding, it approaches this value of E. That's why that PERT formula shows up.
Whatever can be.
It's just approximate. Okay. So as you use this, it's nothing more than substituting into your calculator. Okay? Excuse me. What do you get? $7,389 and 6 cents. Wow.
That whopping 6 cents.
Wait a minute.
You don't get that.
I don't even have the first
Also
one.
slavery.
I'm trying to.
And we know you can press buttons.
Miss AJ.
There's 2.
How is that a cent?
And then you can keep, oh, you're talking about
I get it, cents.
Maybe I don't have any cents.
So you have the 6 cents.
Scary?
Hurts the terrifying.
Are we gonna have to distinguish whether or not we're using,
That guy hit that bank.
And like I said, it'll say compounding continuously. It doesn't say that. Last quick example, I'm going to show you how you can figure out a more specific value using your graphing calculator as opposed to that boundary, how we're doing like between 3 and 4 years or something like that. I'll show you how you can find a real nice, easy number here. Yes, sir?
You know how we had to work backwards for one of those problems? Would something like that be on like the quiz, like a trick question version of PERT?
Well, the trick question version of PERT, I mean, you can still get your amount. Because e to the RT is just some crummy decimal. You solve for your principal, you just drop it and divide it out. That's all. In this case here, I'm going to walk you through how. Come on, we got a couple minutes here, guys. What happens in this case, they're saying that your value of t is the model after 1972. So it means your initial year, when t is 0, is 1972. So what is your initial amount given in this model? 119.6. Okay, because that's your principal amount, so what they're starting with. Yes, I know that if you read it further, it's talking about species. I know you're not going to have a 0.6 of an animal, but you can just say it's about 120 animals. Okay? Now, what they're asking you here is what is the number of endangered species in 72? I'd say it's about 120 of them. Okay? Just because I'm not going to have a 0.6 of an animal. Even though you could buy half a cow.
for me, if you don't want a whole cow, you can just buy half and keep it. My family's
I feel like Tom
Do you
is
have like
thinking like a
big
live
dish
cow.
Well, they feed the cow a grenade and see what happens.
It has 4 stomachs, so it isn't this
Use the graph to estimate when the number of species reached about 1,000. Now, yes, you would be. Now, again, what happens here is that you would put this function into your calculator. And we're going to check, what was it, 119.6 e to the, I forgot what it was, 0.0917. No, point. And I'm going to go to my table, and they're asking me for about when does it reach 1,000. So you would just scroll through looking for when it occurs.
It occurs at around 16.
I got 24.
Should be about 24.
You almost got it.
Between 23 and 24. So that means that the number of years after 1972, it would be, what's 23 plus 72? So somewhere between 1995 and 1996, the number of animals was about 1,000. Okay? Now that's a pretty big parameter between those 2 years. what you could do to kind of get into it a little bit better is find the intersection on your graph. So what I'm thinking here is, do you guys all agree that if I'm looking to intersect something at 1,000 with this curve, it would look like the curve's going up and you've got to hit 1,000 here? You agree?
Yeah.
So let's change our windows. We know that it occurred somewhere after 23, right?
Yes.
So we change my X maximum to 30. And I would change my, and we know we wanted to hit 1,000, so we change my Y maximum to 1,100. Now, go back to your Y equals, and let's put in that horizontal line at 1,000. So in the second line where it says Y sub 2, let's put in 1,000. And now graph it.
Wait, what did you set the maximum and minimum to?
X maximum at 30, your Y maximum at 1,100.
Oh, wow.
Okay? Does everybody see where they're intersecting there?
Wait.
Now, your calculator will calculate the value of the intersection point. Second, calculate number 5.
Wait, 30 and 1,100?
Yeah. And hit enter a few times. And it's telling me that it intersects at 23.158 and change. Now, if you want to be absolutely rambunctious, you could take that, it's after 23 years and some amount of days. Well,
We're not,
0.158151 times 365 gives you about 57 days. 57 days after the first of the year is February 26th.
I got that.
So February 26th of 1995, it works.
Wouldn't it be 94?
No, it's 95.
You can find the
You
exact,
can get really specific going through it this way.
you can find the exact milliseconds. that
Do those, please.
Species all that.
Alright.
No, that's
We'll go over a bunch of this again tomorrow, do a couple more word problems, and call it a day.
Oh shit, my handwriting's gonna be really good on this one.
We may hope.
But where the pencils for you? They're right here, Dan.